All right, here's a third example for what I believe is supposed to be class 17, which is a review of dynamics for acceleration, rigid body mechanics here. And this is another excerpt from my book here. I decided to, in there I used a Huecken, which is very much the problem that you have in your homework assignment. So there you go. And this is a Huecken straight line mechanism, and the position that I've shown here, the crank is in line with the ground, and so therefore the point D is along the straight line area right there, the straight line part. And I've given the crank a angular velocity of 10 radians per second, angular acceleration of 2 radians per second squared. And we want to find the velocity and acceleration of point D. So I consider this to be sort of like a really practical problem to try to find that acceleration. The first thing I want to do is a position analysis. So we're in the fortunate condition that we, a lot of times it's difficult to find the angles that are unknown because, as we've learned, we have those two simultaneous equations, and we have the angles we want to find are in the inside of the cosine or sine. So we have a difficulty trying to solve those, and we have to either use a long algebra method or maybe use the Newton-Raphson numerical approach. But here it's aligned. We could find, using the law of cosines, we could find these unknown angles. Because we know all the lengths in this condition, we're able to find this theta, what I'm calling theta BC right here. And so I find that's 53.13. Well, hey, turns out that's a right triangle. That's probably a 3, 4, 5 triangle. I recognize that those angles. And then we also can find the interior angle beta. It has to be the same thing because, it turns out this is a isosceles triangle. Is it equilateral triangle? I think it's isosceles triangle. I think that's the right word. And then we can, from those two angles that we know, we're able to find the third angle. So we have all of the angles, and we're good to go. Now, from the instantaneous center of rotation method, we do a velocity analysis, and it turns out that just magically, let's see, did I say magically? No, it's not magically. No, we find out what the length, right, of LAB, right, and that is LAB. Where'd you go, AB? Okay, yeah, right here. Okay, so that's the input. Sure. That's what we're doing right here, is we're finding this velocity. And we find this velocity, and then we can find what the angular velocity of BC is going to be, because we take this known velocity right here and we take this length right there, right? So that's going to be the length. That's just LAB and LAE, right? Which we knew up from right in there. And from that, we're able to get what the angular velocity of BC is going to be. And it's the ICR actually lands on turns out it lands right on point E for this, which is convenient for us. So we're able to find that this other this guy right here, he has the same angular velocity. It's just at this particular instant, the ICR happens to land right there. And then, so the velocity of point D can be found, even though I don't necessarily think that we needed that. What we really needed were the angular velocities of the parts. Now we do the acceleration analysis of the, okay, so once again, we did the position analysis, the velocity analysis, and now we do the acceleration analysis. And that's pretty much what we've been doing in this class, right? The order in which we did, we dealt with position, we just dealt with velocity, now we're dealing with acceleration. And so we could find the accelerations of point B right here of this crank. So we start off with the crank linkage, and because we know we were given the angular velocity here, and we were given the angular acceleration, and it's nice and convenient that these are aligned with the x and the y, so that the x is the normal and the y is the tangential. Then we go to rocker CE, so we skip over and come over to this guy and do an analysis of him. Now they do have some angles. We could find out what the values of the tangential and the normal are right here. So we do that, and then but we don't know this angular acceleration, so we got to keep that for a little bit. So we get the acceleration of point C in the x direction is going to be it's going to be a portion of the tangential and a portion of the normal, and we work that out, and now we have an equation, and so I'm calling this equation 1 right here, with an unknown of theta double dot CE. We do the same thing in the y direction, and we're able to get another equation right here. So we got two equations, but we have 4 unknowns right there. So we have AC, x unknown, angular acceleration right here of this is unknown, and the angular and the acceleration of c in the y direction is unknown. And so I guess it would be 3 unknowns. We have 2 equations and 3 unknowns, excuse me. So we go over to the coupler BC so now we use this diagram, right? And we write out what the acceleration is going to be at point C right here, and we're using B as the reference. So we write all this out, and making sure that we're only doing stuff in the x direction here. So we start with the x direction and march through. We know this value of B right there, right? So we know what this is that true? See, actually, but this is mislabeled. No, it's correct. We know. Okay, so here's what we're looking up at this point. So we don't know that. We do know this right here, so that's the 100, and then we take the components of the normal and the tangential, but only in the x direction, right? So let me slow down here and zoom or put this together, right? So this is going to be in the, so this is the tangential x component right here. So that's theta double dot BC right here. That's the thing, and we don't know this either, by the way. And so we want the x component of that. So it's really going to be that guy there. Maybe I'll draw him up right here. We want that component right there, and we're taking the sine of that BC, right? Because that's inside that angle right there. And then we also have the x component of this guy right here. So that's going to be the horizontal, and it was going to be negative, right? Both of these are negative because they're both pointing to the left up here. And so theta dot squared times BC, that's what this guy is equal to, and times the cosine of BC, so it's only the x direction. And we work that out, and now we have another equation right in here. But we have 3 equations, but now we have an additional unknown, that BC. So we got to keep going along. And then we go for the y direction, and so that's going to be taken up like right up here, and we write the thing out. We know that this is going downwards right here, and This component is positive because it's upwards, right? So let me switch colors here so I can highlight that. So that's going to be this component right there, right? So that's why that's positive. And then here I get another color, go green. And then this one right here is going to be downwards, right? So that's why that one's negative. And so now we're left with another equation. So now we have 4 equations and 4 unknowns. So, but you notice that AC and ACX and ACY, ACX, ACY, we can substitute those back in, equate those, and so now we have this equation to combine right in there, and we can solve for one of them. Yep. And so I solved for theta double dot BC. Do a little bit of math, stick them in there, and then solved for theta double dot CE. And then once I knew that, I could find, if I wanted to, the acceleration at C. But I didn't really need that, so I didn't solve it. My main goal in all of this was to find the acceleration over at D, right here, I guess, over here. So that's what I proceeded to do. What I really needed was were these. I needed to know theta double dot BC and theta double dot CE in order to get these. So I placed them in here, and I'm able to find because I'm using B as the reference again. So once again, I'm using this this diagram, but now I'm focused up on here, right? And so I'm still using B as the reference because that's the thing I was given, or not the thing I was given, is the thing I was able to find from this right over here. And so I'm able to find the acceleration at D in the X direction and in the Y direction. And ta-da. It's a long process. It might be like really annoying and maybe a little overwhelming if you haven't done one of these problems in a while. But walking through, you should be able to understand the logic at how we came up to that answer. I don't think I'm gonna ask any problems that you have to do this, because we're going to use the methods within our textbook within Norton. But this is really the connective stuff back to dynamics, not necessarily the method that everybody uses when covering dynamics. There's a number of different ways to approach kinematics problems, including just using vector math. And so many courses, that's the only way that they teach it. I like to have a little bit of a mixture, but I prefer this this method when teaching dynamics. I call it the 3-diagram method. So we can get rid of all this stuff and discard it so it doesn't save onto the thing. And many minutes is this? 13 minutes. So today's guitar is a weird one. I'll probably actually use this I'll probably have this one in class. This is a strange one. It was relatively cheap, only like about $200. It's Ibanez, but this is like the lower end of Ibanez. But it came like this right here with this built into it. And this is a Chaos, mini Chaos pedal or Chaos. I don't know what the hell they call it. It's an effect. So it's like some people, especially electronica musicians, use this thing. But anyway, we'll turn it on, and you see that it's powering up right here. And it's hardwired into the guitar. Well, not hardwired, it's actually loose wired, I guess, into the guitar. And it has a whole bunch of different presets. It's got a pad. You'll see that's got like a XY pad that you move your finger across right in here. And this also has a distortion pedal built into it, a distortion circuit built into it, so it can drive the Chaos pedal. And like I said, this is a poor, not a very well-made guitar. I'll bring this down here so I can kind of demonstrate what's taking place. And so let's see. Did I turn this off? Why aren't you making noise? Huh. What happened here? Why aren't you making noise? Oh, the tuner's on. All right, so this is, I put it through, I have it a little dirty. That's the amplifier simulator. But here's where I turn on the, flip the switch for my distortion. See, there's, without the distortion, with this. And then I turn the thing on now. Now some of these, I got a bunch of different settings on there. It's called a low pass filter, high pass filter, band plus filter. What is that? Some of them sound very similar to me. It's called a vowel filter. So it sounds a little bit like. So it's a little bit like you're talking, just a little tiny bit like it's talking. This is a mid isolator. Don't know what that does. Some of these are meant to use with a microphone and that kind of thing. They're not. This thing was not built for this purpose right here. This was an add-on thing. Oh, I think the batteries just died. Yeah. You can see that this thing is falling apart. It's a piece of crap. I left some batteries in it at one point that died. So I think it still has some of the gunk from the exploded dead batteries in it. These might work. I don't know. Some of these batteries are good and some of them are bad. This is the kind of chaos I live with. Let's see if let's see if it'll turn back on. Otherwise, the video's over. The Chaos, Mini Chaos 2 or something or other. I don't know what the hell it is. Okay. Well, it seems to indicate there's more battery in there. I like there's a couple in here. Okay, so there's some delay in there too. The one I like the best is the vinyl break. There's also a couple. Some of the flangering things sounds kind of cool. It's really trippy. Manual phaser. This is supposed to be a talk filter. I don't even know. I don't like that one. Ducking comp, low comp, hard limiter. I'm trying to find fuzz distortion. Here you go. Bass distortion, ring modulators. What does this one do? Someone really sound like the same thing. It's kind of fun, but I'd never play this out in a band. That's enough of that. So anyway, there you go. An interesting and totally waste of money, useless guitar. But kind of fun. I don't know. So wasted a lot more of your time.